All right, so I'll go ahead and get started. My name is Amy McAdam. I work at NASA Goddard Space Flight Center, and I'm going to go over today some examples of observations from Curiosity that give information about the record of Martian environmental history. Next slide. So over the last 5 years, Curiosity has traversed a significant distance in vertical section, and she has made a variety of observations that have allowed inferences about past environments at Gale that have included lake environments, river environments, and alien environments. And an example of a key geological and geochemical, in this case geochemical observation that Curiosity has made is depicted in this progression of pie charts, which shows the mineralogy of several mudstone samples that have been analyzed by Curiosity, and this mineralogy was determined by Curiosity's ChemIn mineralogy instrument. Trends and differences in the mineralogy changes throughout the traverse allow us to place constraints on characteristics of the rocks and inform environments such as sediment source regions for the rocks, their formation processes, and their later alteration processes. Next slide. So results from the Evolved Gas Analysis mode of the Sample Analysis at Mars Instrument Suite, or SAM EGA as I'll talk about it, also give constraints on the diversity that we've seen in mineral samples in rock samples throughout the traverse. Each EGA analysis produces a lot of information. So here I'm just showing examples from several key volatiles, and then just from two of the samples, two mudstone samples that SAM has analyzed of the total of 15 that have been analyzed so far. This mode of operation gives you data like this that shows you various volatiles that are evolved versus temperature, and what volatiles you see and their evolution temperatures can give you constraints on various things about the sample. So you can understand the nature of the significant X-ray amorphous material that has been found in all of the samples analyzed by Curiosity with these instruments so far. And you can also get constraints on trace minerals that are present in the samples. So for example, the oxygen evolutions that you see at some temperatures are indicative of oxychlorine phases in those samples, like perchlorate and chlorate salts. And the specific temperature of evolution can give you constraints on which specific chlorates or perchlorates are in the samples. HCl that we see, I don't have it plotted here, in these analyses also can come from those types of minerals as well as chlorides. Water at low temperatures can be adsorbed water, but at higher temperatures can give you constraints on hydrated or hydroxylated minerals in the samples. For example, the distinct peak that you can see at about 450 in the lower plot results from a mineral called jarosite that will come up later in the talk as well. CO2 in the samples can come from the decomposition of carbonate minerals in the samples and also from oxidized carbon or the oxidation of organic compounds. I won't go into that in detail because the talk right after me will talk about organic observations. SO2 and H2S can be from sulfates or sulfides in the samples. And finally, NO, highlighted in red, indicates the presence of nitrate salts in these samples. And this was interesting. This is the first in situ detection of nitrate salts on Mars. Next slide. So in addition to providing information on the volatiles evolved from samples, on heating them, data from SAM, in the context of other data, has also enabled constraints on the isotopic composition of these evolved volatiles. So here is an example of a measurement of the deuterium to hydrogen ratio in some water. So a little background. So clay minerals have an OH group in their structure, and is evolved at high temperatures as water. And so SAM performed a specific stepped heating experiment to target this high temperature water evolution. And the reason was because this will represent the D to H, or deuterium to hydrogen ratio, of the water that the clay mineral formed in 3.5 billion years ago. So we expect, as water is lost from Mars over time, that the lighter isotope of hydrogen will be preferentially lost, and this D to H ratio will increase over time. So the value obtained by SAM is shown here in this middle dot. And that value, in the context of the D to H ratio of water evolved from older rocks, from some Martian meteorites, and also the D to H value of water in the Martian atmosphere, together all of this allowed a constraint on the amount of water lost from Mars to tens of meters. So this measurement provided this important constraint on changes in Mars's water inventory over time. Next slide. And so here's just another example of an interesting constraint on water inventory. an analysis that Curiosity did of the Mojave Mudstone sample. So this mudstone had a significant proportion of that mineral jarosite I mentioned a little bit earlier, which is potassium-bearing and is a secondary mineral. So it forms through water-rock interactions. So its presence indicates past water-rock interactions recorded in this rock. And potassium decays at a known rate to argon-40. So if you can measure the amount of potassium in a sample and the amount of argon-40 in a sample, you can determine its formation age. So with Curiosity, we used the Curiosity APXS instrument to measure the amount of potassium and a stepped heating experiment to measure the amount of argon-40. And this enabled determination of the formation age of that jarosite. So in detail, this detailed work requires understanding and consideration of all the other phases in the sample and the argon retentivity and things like that. And actually, for those details, I refer you to a paper by Peter Martin et al., which is in Press and JGR, and also Peter Martin's around here somewhere. But the upshot is that the age of this jarosite is at least very likely, at least less than 3 billion years old, which sounds old, but it's really young for Mars for fluvial activity. That would postdate the lake we think was in Gale crater and most fluvial activity on Mars. So next slide. And so thank you for listening to these little vignettes and examples related to Martian environmental history. So we'll continue to take measurements like these and many others that give constraints on these, and please stay tuned for more analyses by Curiosity, and I'll take any questions.